So today I want to introduce the concept of metabolism. We have been hinting at this phenomenon that happens in the body once a drug is taken up. And it's basically evolved as a natural system to detoxify the organism. Obviously, organisms have not evolved to detoxify from aspirin per se, but we know we have evolved to detoxify ourselves from food, basically. And so we'll see that the enzymes that are part of the metabolism have a final purpose, which is to facilitate excretion, so to get rid of compounds that are perceived to be extraneous to the bodies or possibly noxious or possibly harmful. How do we do that? Well, we do that by using a series of enzymes, so they're all enzymatic reactions that have the purpose of making the substrate more polar, increase water soluble, make the compound easier to eliminate. And as we'll see soon, the main elimination route is through the urine, so it's mediated by the kidney. And in general, compounds that have high polarity, high water solubilities are easier to eliminate. And so metabolism has the purpose of taking something that has a low water solubility and transform it into something with high water solubility. If you remember one thing about the metabolism, this is it. Most of the metabolism, as we know it, happens in the liver. And so what we'll consider here is a schematic of blood circulation and the main organs involved in metabolism and blood circulation and excretion. So we have the heart, which obviously is the pump, which drives the whole system. The lungs, which is obviously where blood gets oxygenated, and so where we go from arterial system to venous system, or rather vice versa, from venous blood to arterial blood. The GI tract, which is where we are ingesting drugs or food. And then anatomically, the GI tract is connected directly to the liver through the portal vein, which collects all the blood vessels that irrigate the GI tract. So the liver is the place where the so-called first-pass metabolism happens. So the liver is the first organ that sees the food or the drugs that we ingest and deals with them in somehow. And then we have the kidney, which is where drugs or other compounds, so where the bloodstream gets filtered and where drugs get filtrated out into the urine and therefore eliminated. This is a very schematic view of the human body, obviously. There are other ways of absorbing drugs, as we have seen, but in the end, all drugs end up in the bloodstream. There are other ways of eliminating drugs from the organism, not just the kidney, but we eliminate them constantly through the skin, for example, through any fluid like breast milk, feces, and anything else that leaves our body. But this, if you can remember this schematic, helps us also understanding how the biggest hit that a drug takes after being taken orally is through the first-pass metabolism. So right away, goes through the liver, and a big chunk of it will get metabolized and eliminated. We distinguish into two phases of metabolism, phase 1 and phase 2. So phase 1 is formed by the chemical modifications to the drug, which are typically oxidation, reduction, hydrolysis, where the drug gets converted into a derivative. This derivative then is conjugated to another molecule to generate something that is easier to eliminate. And so And we'll hammer this concept in this module extensively, but phase 1 is chemistry, transforming a functional group into another functional group. Phase 2 is chemistry too, but it's conjugation chemistry, is where a drug gets covalently linked to another small molecule. Aspirin is a great example of that. So we start from what we had defined as a prodrug. So there's a compound here, aspirin, which gets hydrolyzed here at the ester moiety, right? And we get salicylic acid, which is the active principle, by the way. So that's the active component of aspirin. Salicylic acid then can be conjugated to glucuronic acid to form this molecule that is now very hydrophilic and very easy to eliminate. So that's in a nutshell all the pathways of metabolism, and what we'll do in the following lectures is talk more extensively about what happens in phase 1, what is the chemistry that goes on, where these enzymes are located, and typically will be in the liver, and the most important one will be cytochrome P450. And then we'll talk about all the small molecules that can be used for these conjugation reactions in phase 2. Let's also connect metabolism and activity. And so this is a very complicated system. We'll start from a drug, and then we'll convert it into several metabolites, and those metabolites will interconvert among themselves. And we have 3 possible types of metabolites. Metabolites that are still have an activity and are potentially toxic. Those are often reactive metabolism. We will see some examples in the next slides. We have metabolites that have similar activities to the drug that was the original drug. And those are, the most neutral ones because they don't really change much from what the drug was doing. And then we have the inactive metabolites, so metabolites that have lost the pharmaceutical activity, and so any usefulness really of the drug. There's a complex interplay between these pathways, and so from the drug we'll go into the various metabolites. We have reversible metabolism in which a drug is converted into another one and then eliminated into a metabolite and then eliminated. Sometimes from the metabolite number 1, the first level, we can reverse it back to the structure of the drug. And this can be done either chemically or by using 2 different enzymes. A drug can also be eliminated unchanged. A drug can be transformed to a metabolite that then gets metabolite again and then gets eliminated. And so this complex interplays helps us understanding how complicated the life of a drug is in the body, and all the compounds that we have to consider, for example, for toxicity of a drug. It's not enough to know what is the toxicity of a drug, but we need to consider and characterize the activity and toxicity of each of the known metabolites. And that's part of the paperwork that we have to submit for FDA approval of a drug. We need to know what happens to a drug in the human body in its totality, and we need to keep track of all these metabolites, both in terms of quantities and activities and lifetimes. So let's consider a few examples of chemistries for phase 1 metabolism. The 3 main classes of reactions that we'll see are oxidation, reduction, and hydrolysis. Oxidation can be done at several levels, and so in organic chemistry in general, oxidation is the introduction of oxygen. And so we have compounds that get dealkylated at the N, so at the amine levels, or at the oxygen, so in ether, We have desulfuration, so for example, transforming a sulfur into an oxygen, and so on and so forth. This is an example of what happens to thiopental, which is an anesthetic agent. It's part of what we use during anesthesia. The sulfur gets taken out and replaced with an oxygen. And this changes completely the properties, the hydrophobicity of thiopental, and changes its lifetime in the organism. Then we have reduction, and this example of reduction can be going from a nitro group, for example, to a primary amine. And this is what happens to chloramphenicol, which is an antibiotic, which is metabolized this way to make it non-effective anymore. Examples of reduction of the carbonyl group is here, where a ketone can be transformed into alcohol. This is, for example, what happens in warfarin, which is an anticoagulant drug, which has a very long lifetime, and gets reduced to alcohol and therefore eliminated more easily. Let's do a little overview of what happens in phase 2 metabolism. As we discussed, phase 2 metabolism is the ensemble of all the conjugation reactions that can happen to a drug or its metabolites. And so the first example is the addition of glucuronic acid to a drug, so the glucuronidation reaction. This happens on a number of substrates: phenols, alcohols, carboxylic acids, hydroxylamides, sulfonamides. And this happens, for example, to acetaminophen, which is an analgesic and antipyretic agent, which I think most of us are familiar with. So this is the structure of acetaminophen. In the presence of UDP-modified glucuronic acid and an enzyme, which is a glucuronic acid synthase, acetaminophen is conjugated with the glucuronic acid, which is now eliminated. So one important thing to remember about these conjugation reactions is that they are catalyzed by enzymes, and they typically cost energy because they typically modify our metabolite with a pre-activated compound. In this case, the glucuronic acid is pre-activated by bonds with UDP. Another type of phase 2 metabolism is acetylation. This is what happens to this sulfixoxazole, which is an antibacterial agent, very complex, and it gets acetylated, this moiety here, the primary amine, to form this drug. Acetylation happens by using acetyl coenzyme A, so where the acetyl group is activated by the coenzyme. And so again, energy expenditures and use of enzymes for the reaction. Another type of conjugation that happens is with glycine or other small amino acids, and that is carried out on carboxylic acids, such as salicylic acid. So glycine can be conjugated to the carboxylic acid to form this molecule here, and now the molecule is eliminated more easily because it can utilize its transporters for amino acids. This is also a reaction that costs energy, and as we'll see, is a little different from the others in that it is the carboxylic acid that gets activated and not the amino acid. Finally, we can attach a sulfate ester to phenols and alcohols and aromatic amines. We'll do that with a compound called PAPS, which is again an activated form of sulfate. And this happens, for example, of methyl dopa, which is an antihypertensive agent, so lowers blood pressure. And we have here the modification on this hydroxyl group to something that is now much more water soluble. And again, we have enzymes and expenditures of energy. Another way to eliminate a functional group is done by methylation, and so we use this as carried out on phenols, amines, and thiols, and it's done with SAM, which is S-adenosyl methionine, which transfers a methyl group to the OH group here. And that's one of the ways by which adrenaline is rendered inactive. So we talked about metabolism as in general increasing the excretion of a drug, but in certain cases, actually, metabolism also deals with eliminating functional groups and rendering a certain drug inactive. And this happens in adrenaline, for example, which is obviously an endogenous compound, so it's already present on the body. And so methylation kills the activity and therefore regulates the lifetime of adrenaline in the bloodstream. All these various metabolisms have a very complex interplay. Phase 1 metabolism and phase 2 metabolism can happen at the same time, or can happen directly on the drug, or in a sequential manner. For example, acetaminophen, our compound that we already seen, which is an analgesic, can be metabolized by phase 1 reactions in various ways, oxidized to this compound, which is very toxic, is a quinoneamine. And this toxic compound is eliminated by glutathione. Glutathione is conjugated to the, basically attacks here this position to restore aromaticity in the aromatic ring and render the compound non-toxic and inactive. So in other words, it acts as a reducing agent. Other things that we can do to acetaminophen, this is cut here, but basically is to conjugate it with sulfate and render it inactive this way. We can also directly from the drug add a glucuronic acid and render it inactive by this mechanism. So this is an example of the complexities of metabolism, and still quite simple. And again, when we deal with a certain drug, we'll want to understand how the drug is transformed in the body and what kind of compounds it gives rise to.